In this video, we will have a look at creating pocket milling toolpaths in Grasshopper. This video is a very simple example. There's much more that you can and probably should do if you actually want to mill material. Depending on the material, you might need lead-ins and lead-outs. You might need more control over the toolpath or roughing toolpaths and then finishing toolpaths. But in this video, I will just go over a simple toolpath of how we can create the horizontal offsets, these concentric offsets, but then also the vertical offsets that allow us to cut at steps of a specific depth. We have a base geometry, which is this rectangular 3D geometry right here. We have a pocket geometry, which is our negative geometry that is subtracted. And we use this to then create our solid difference, create polyline offsets, which we then offset in the vertical direction. You can find this template in the link in the description. And you can follow along with the tutorial if you actually want to understand it and actually get enough knowledge to change it in such a way that you can use it in your own projects. All right, so I have two pieces of geometry. One is just this rectangular piece right here, and the other one is this angled cylinder. And one is my base geometry, so basically the positive material, the material stock that I'm starting with. And the other one is a negative geometry, so the geometry that is taken away from my base geometry. And as you can see, they intersect. And if I use a solid difference component in Grasshopper, I can see that I can cut out this piece from the base geometry and I can see what my result ideally is. Now, in order to create this, we need a bit of information from our geometry. And the first piece of information is the angle of this surface right here. Depending on your machine, you might just want to do a planar 2D slot. But if you're using Grasshopper, chances are you're using a more advanced machine. So for example, a robot or some sort of 5-axis CNC 3D printer or some other machine. So I'm guessing that you have some interesting geometry. And so I've angled this pocket just to make it a bit more interesting. But if you have a very simple pocket, the process is pretty much the same. You can skip a few steps, but you should be able to follow along just fine. So in order for us to find this surface right here, the surface of our pocket that we need as an input, I will use a very simple method, and I will use the deconstruct brep component, use my pocket geometry as an input, and with a simple list item component and a number slider between 0 and 10, I can then simply get the correct face of the brep. And in our case, this is a flat 2D surface. It's at an angle, but it's still a flat surface. So the result is a surface. Just to make this clear, I will use the surface param. But since it's flat, I can simply cast it. Casting just means converting one piece of data into a different kind of data. In this case, a surface cast into a plane. And I can cast it to this other piece of geometry, so I can simply create a plane from this surface. And since this is a circular surface, the plane is also placed right at the center. With other kinds of surfaces, this might not be the case. The plane might be at a different point, but this should not really change our process because we simply need our direction vector, the z-axis of this plane. We're not really interested in the location. So the next thing we need is the outline of this surface. And we could also just cast the surface to a curve and get the outline, but I will do a bit more complex way of getting the correct edges. And I will do this by simply using the deconstruct brep, or even better, I can use the brep edges command and use the naked edges which in this case is already just one circular curve. But if it were multiple curves, I can simply use a joint curves to create one curve from the outline of my surface. So now that I have this one curve, I want to offset it multiple times inwards. I will first just do the offset, and then I will go over how we actually set the different parameters that we might need in the offset. So in order to offset our polyline here, so our outline curve, sorry, I will use a component called polyline offset, and this component is part of the Klipper plugin. If you don't have the Klipper plugin installed, you can install it with the package manager in Rhino. And here you can simply search for Klipper. I'm using the Klipper 1 plugin. It's a bit simpler than Klipper 2, but it has the component that we need, and it's also a bit easier to install. So if you want to follow along, simply use the Klipper 1 plugin, and I will use the polyline offset component. So the curve we just created is our polyline's input. Even though it's not a polyline, this should still work. And next I can create a number slider just for testing between 0 and 100. And I will see that this already works. I have my base curve, and I can then offset inwards and outwards with the number slider. Depending on your geometry, you might have to add the plane input. The plane input we just created. I just noticed that in our case, we actually did not need it, but sometimes you need it. So it's also good practice just to add the plane input right here. Now, of course, we don't just want to have one offset. We want to have multiple offsets that define our pocket. And I will just create a quick drawing to show you how we want to define these offsets. So imagine we have our pocket geometry, so just the curve that defines our pocket. And the first offset that we need is actually half of the diameter of our cutting tool. So imagine the cutting tool having this diameter. And of course, we don't want to simply have our cutting tool cut on the outside of this circle. We want it to be offset to the inside by a specific amount, and that is just the radius or half of the diameter of our cutting tool width. So this is our first offset. So our first curve goes along the circle at this distance. Now, depending on what you're cutting, you can also just continue using this offset and basically offset the cutter by half of its diameter every time we go further inwards. But sometimes it's also good to have multiple steps that are smaller. So some steps that are just slightly smaller, maybe a quarter of a diameter, and to change the distance that we are going inwards at each step, just to make sure that we're not taking too much material and the cutter can actually keep up with the amount of material that we want to remove. I hope this makes sense. There's a lot of information about CNC technology and CNC cutting strategies online. So if you Google for it, you should find a lot of information, a lot of instructional videos that will tell you a lot about the different parameters like step overs, depth of cut. I will not go over that here, but just so you understand what we're doing. So in order for us to not just set this offset distance statically with a number slider, we actually need a number slider, and I will add a number slider from 0 to 50. And this number slider will not be just something for us to set by feel, but instead it will define the cutter diameter. And so this is the diameter of our cutting tool. I will just set this to 12 millimeters. And now we talked about getting the radius. So I will use a division component, divide by 2, and get the radius. And I don't just want one distance, one offset, I want multiple offsets. And so in order to get this, I will use the series component. And the first offset is half of this cutting diameter. And then the next offsets can be set at a different rate. So I could either do this manually, so just by setting a specific step over here. I could also use another division component that I can use to divide my radius further. So let's say I want the first offset to be half of my cutting diameter and the next one to be half of that. I can then set this second one even lower. And this one is called step over multiplier. Sorry, that's not multiplier, step over division. All right, and now I can use this series as an input to my polyline offset component. And as you can see, we have a larger offset right here. Let me increase this a bit. We have a larger offset right here, and then we have smaller offsets continuing to the inside. We're only interested in the holes. So the polyline offset creates offsets on the inside and on the outside of our curve, but we're only interested in the inside offsets. So I will use a curve param at the holes. And you can also see that there is no option to just automatically create as many offsets as we need. There are ways of doing this, and especially in a circular curve, this is quite easy. But in our case, I will simply add a number slider that should be more than enough, maybe 200. And then I just have enough curves. This is a bit of a crude method, but it should also be enough depending on the geometry that you have. Of course, if you use way too many, this will take quite a while. So make sure you're not using a crazy amount, but just enough to fill the entire geometry with offset curves. I will also reduce the amount of offsets just to decrease the amount of computation that we need. Let's say our first offset is the radius, and after that we have half of the radius. All right, so now that we have our offsets, we actually want to move them in Z. But of course, this is not the global Z, but we want to move them in the local Z vector, the one that we got from our plane. So in order to get this vector, we will deconstruct the plane we created. Get our Z-axis. And the next thing we do is to create an amplitude vector. Sorry, to create an amplitude component. And now that we have this amplitude component, we can create another series. To create multiple vectors. I will then use a move component, and the offset curves are my geometry, and the motion is my vector. And it's not that easy to see, but let me increase this just a bit. But we have now offset our curves, our offset curves, by a specific amount. Here we also want to just add a number slider that gives us more offsets, and another number slider, for example, one that goes from 0 to 20.0, which will define our depth of cut. And this depth of cut is our step in the series. And so we created just a whole lot of offsets. Now, the amount of offsets that you need is, of course, dependent on how far away or how big your actual base geometry is. So now we created way more than we need, but we can then use our base geometry, so the one without the cut, as an input to trim away all of the curves that we don't need. So in order to do this, I will use the intersect trim with brep, use my base geometry as the input brep, and use the curves we created as the curves in the input. And now we get two lists, inside and outside. And if I use the curve here and check the ones outside, I get the ones on the outside, but we're interested in the ones on the inside. Again, I will increase these distances just to make it a bit more clear what is happening. So now we have the ones that are just where we need them. So just the curves that are actually necessary to cut away the material that we need. These curves are not closed. In our case, I just use the close curve component. To simply create closed curves from that. And now that we have these curves, we get this error because we have lists in our trim that are empty. So you can see that there are a lot of empty lists. So I can use the clean tree component with a Boolean toggle and simply remove all of the empty lists. And then we should also not get any issues here. If curve is already closed, it cannot be closed again. Okay. So now we are sure that all of the curves here are closed. And the next step we do is to get points from these curves. Currently, these are circular curves. Some CNC machines can also use circular curves directly, but I still want to create XYZ coordinates. So I will need to create points from that, and I will use the curve to polyline component because this component gives me a lot of control over the tolerances. So it will look quite weird in the beginning. The curves have been distorted quite a bit, but we can use the tolerance input in the curve to polyline component to choose how much tolerance we need in our polylines. In my case, I will just use 0.1 because it's enough. And now that we have this, I can use the control points component and look at all the control points we have. And if I were to decrease my tolerance, I would get more points. And if we were to increase my tolerance, I would get less. But of course, the polyline would also be coarser. So now that we have the control points, we can create planes from these control points. So if you are using a robot, for example, you would need to create planes. And we already created our plane right here. And so we can use the plane origin component, use the plane we created as our base input, and use the points as our origin. And now we have the points or the planes we need to cut the pocket at the angle that we need. There are a few things we still need to do. Depending on how you created your offsets and created the vertical offsets as well, we might have the curves might be in the wrong order. So right here, we started from the bottom. We started from the bottom of our pocket and then offset upwards. So in our case, this would be the wrong way around. So what I would want to do is to reverse this list just to make sure that we're actually cutting from the top to the bottom. This probably wasn't enough. I'm not entirely sure how the list looks, but this is probably just a step too much, and this tutorial is already getting kind of long. But it is important to look at the order of lines and curves when we're sending them to a machine, because of course we want to start from the top and work our way into the material and not crash into the material and work upwards. So we created the curves, and if we created our system correctly, we can also use different geometries. So for example, I created this pocket, which is just a 2D pocket with a slightly different shape. And hopefully we get valid curves directly from this. And as you can see, this seems to work. And now we can use any kind of BREP input for our pocket geometry. Of course, this toolpath now is super simple. There is no lead in, there is no lead out. There are no spiralizations, there is no helical spiral that actually like goes into the material to remove some material first, but it's just very naively just going into one layer, cutting away the layer and going into the next layer. For some materials, maybe a soft wood, this could be enough, but you often need more complex toolpaths than this. But this should give you a good start and a good understanding of what you need to get started, and then you can expand on it and get more complex if you need it in your process. I will clean this up, and you can find the link to this template and also the other milling strategies that will be in this template in the description below. And there we will find a website where there's a bit more information and also the download link for this template. If you have any questions, you can leave a comment, and I will see you in the next video.